when you read question 10, the velocity of an object after t seconds, so we've got a velocity function, so I just think this is not displacement, all right, it's a velocity function, I'll fix that in my mind. It says use technology. Now, as I've said many times, I prefer Desmos because the graphics calculator, if you don't have a good view window, is very messy. So before we go to the calculator, it's really important to get a bit of an idea what values the velocity might take. So just do a couple of calculations. And you could actually use your calculator to do some of those calculations. So I've entered the exponential function into my calculator and I've got the view window at the initial screen. X is -6 to +6 and Y is -3 to 3. Now with an exponential function, or actually this is a surge function because it's got the variable t times e to the -2t. I'm not thinking that view window will be suitable, but if you draw the function, so even if I can't see it very well, I've drawn it. Now I can go Shift G solve and I can find some values of y. So if I calculate when x equals 0, it will tell me that y is also 0. So let's just put a couple of these points down. Ooh. So we've got 0, 0 as a point, and the domain is greater than or equal to 0. So let's try a G solve. So Shift G solve for an x value of about 5. So we want to calculate the y value for an x value of 5. And we find out that y is 5.7. So let's see if that's enough to get a decent graph. So if we go Shift View Window, the minimum is 0. Let's go up to 10. We want to go down to the Y minimum. Well, let's just guess that it's increasing from 0. And it goes, let's put 30 in there just to see what happens. Okay, so it looks like our scale going up to 10 has given us a tiny diagram. So we could go Shift View Window and make it only go up to 7. See if that gets us a bit better drawing. No, it wasn't the x-axis, it was the y-axis. So let's make the maximum in the y-axis more like 10. See if that gives us a better picture. Oh, and it is a surge function, increasing to a maximum and then becoming asymptotic to the x-axis. So we've got technology and we can now draw a sketch. So our sketch, we've got the shape of a surge function asymptotic to the x-axis. We've got a couple of points. We know that that's 0, 0. We've labelled our axis v of t and t. And we've got our units of seconds and meters per second. And we can go back to the calculator to actually find the maximum of the surge. So if you go Shift G solve maximum, it gives a maximum at 0.49, so that's a half, and 4.6. So a half, 4.6. So we need to have a bit of a scale on our diagram. So part B asks us to find the acceleration and actually gives us the answer. So we've got to do the differentiation of the velocity function to get the acceleration function. And we've got to show that we know how and that we know where we're going. So it's going to be a product rule. is going to be, so acceleration is the first derivative of velocity, and it's 25 times whatever we do. So product rule, derivative of t is 1 e to the minus 2t plus, we just put the t there, the derivative of e to the minus 2t is e to the minus 2t, and we take the derivative of the power function, which is minus 2, put it in brackets so it's clear that we multiply it, and we've just got to simplify it. So the 25 is out the front still, e to the minus 2t is actually a common factor, so let's put that out the front, 25 e to the minus 2t, so there's one lot of e to the minus 2t, and there's minus 2t lots of e to the minus 2t. And we just look back at the answer that was given, so we were given acceleration equals 25 1 minus 2t e to the minus 2t. So our answer just has the factors in a different order, and yes, it does equal the given value, AT given. And the units were centimetres per second squared. So when is the velocity of the object increasing? So we need to think about this a little bit. If the speed is to the right, so if an object is moving to the right and it is increasing its speed, so its acceleration is increasing, then the velocity is increasing. But if the object is moving to the right and the acceleration is decreasing, so I just change colour here, if it'll let me. So if I now do acceleration decreasing, and we still have and the velocity was to the right, then the object will be slowing down. Now, the reverse is true. If the object is moving to the right and the acceleration is decreasing, that means negative velocity is increasing. I don't know if I've said that very well. If both are negative, if the velocity is to the left and the acceleration is negative, then the speed is increasing to the left, and a larger negative speed is considered smaller. So the main point, I guess, is the sign of the velocity and the acceleration have to be the same. So let's go ahead and do a sign diagram. So to draw the sign diagram of the velocity will change direction around 0. So negative is to the left and positive is to the right. And to change from negative to positive, you've got to go through 0. So when we look at the velocity function that we were given, I've just written it as 25t, and I've written the exponential function with a positive power on the denominator. So you know exponential functions are positive for all values of t, so e to the 2t is positive. If you reread the question, you'll find out that t is greater than or equal to 0. And in a lot of applications, we do only consider time 0 or greater. Therefore, the numerator 25t, the lowest value it can have is 0. It will never be negative. So the sign diagram for the velocity function is always positive. So it can be 0 at 0 and the rest of the time it's positive. If we look at our acceleration function, one of the reasons we were asked to put it in factor form is If we look back here, acceleration 25 is a number, positive. The factor e to the minus 2t, well, 1 over e to the 2t is a positive number, so that is positive. The only factor that's going to change the sign is the 1 minus 2t. So just write that down. 1 minus 2t is a significant factor. The other two are both positive. So the smallest, if t equals a half, then the acceleration function will be 0. T is greater than or equal to 0. Therefore, if we look at the acceleration function, and I've just realised I've made a mistake here, I need to draw that sign diagram matching it up with the velocity one. So let me just shift it. So I've got my sign diagram on the right with the zeros lining up. And if I put in a value like a quarter for t, take 2 times a quarter is take a half, that will be positive. And if I put 3/4 or even 1, 2 ones are 2, so 1 take 2 is going to be negative. So a negative number times positive 25 times e to the 2t, or divided by e to the 2t, which is also positive, will give me a negative. Therefore, the speed is increasing, or velocity is increasing, for the values of t, where 0 is less than or equal to t, and t is less than or equal to a half. And the speed is decreasing, so part D, the speed is decreasing when they're in opposite directions. So velocity is decreasing, so they're opposite signs after a half. For t is greater than or equal to half, and that matches the surge diagram. Do you remember that the velocity diagram surged to a maximum and then it decreased and became asymptotic? So after a half, and we plotted that maximum, and we found that the maximum did occur when t equals a half. So after a half, the speed is decreasing, and because it is asymptotic to the x-axis, it's always decreasing. So I hope that you can see how to match the original diagram with the meaning of what's going on.